In this video, we'll go over how to normalize relations to third normal form and understand why databases are normalized. When designing a relational database, you need to consider your list of fields and decide which ones could result in repeating data across multiple records. All this data needs to be stored, but repeating data can take up additional storage space unnecessarily. As the database grows, the situation will only get worse. To prevent this problem from arising, we could split the previous table into two separate tables. In the process, we can create a relationship between them. In this example, we would say that a single tutor group can contain many students, and many students can belong to a single tutor group. The relationships that exist between tables in a relational database come in three forms: one-to-one, one-to-many, and many-to-many. However, although many-to-many relationships makes logical sense, they are not considered good practice when designing a database. Each record within a table must be identifiable, so there should be at least one field in each table that can be guaranteed to be unique. This field is called the primary key. If no existing field will make an appropriate primary key, we can either create a composite primary key from two or more fields, or add a new field. There are many ways of arranging data in tables within a database. Each method is labelled according to the nature of the arrangement. These labels are known as the database's normal form. At A level, you need to understand three types of normal form: first, second, and third. The concept of splitting tables in a database and arranging the data to move it from first, second to third normal form is called normalisation. You need to be able to design a simple database up to third normal form. You also need to understand and be able to apply the criteria of first, second, and third normal form. To get to first normal form, a table should follow 5 rules. All field names should be unique. Values in fields should be from the same domain. Values in fields should be atomic. No two records can be identical, and each table needs a primary key. So let's consider each rule in turn. All field names must be unique. We do this to avoid confusion when we come to retrieve or perform any other actions on the stored data. All our field names are unique, so this rule's been met. Values in fields should be from the same domain. So in each field, the stored values must be of the same type. Now this is not true for the lecturer field. We're storing lecturer's initials and their name. This is two different types of data. More specifically, these two pieces of data are from different domains. To fix this, we can split the lecturer field into two separate fields: lecturer initials and lecturer's name. This rule has now been met. Values in field should be atomic. So for every record and field intersection, we should only have a single value. We can see that the fields course number, course name, and course lecturer and lecturer name all contain multiple values, so they're not atomic. All we need to do is split the values up into atomic values. By doing this, a few values are now repeated, but values for the remaining fields are now atomic for each record, so this rule has now been met. We could argue that the name field violates Rule 2 and 3. Ideally, we would split the name field into two separate fields, first name and surname. For simplicity for this example, we'll keep the name field as a single field. We've increased data redundancy. We now have fields with the same data across multiple records. However, each record is unique, so for now, Rule 4 we can say has been met. Now, none of the current fields would be appropriate to use as a primary key. Often, the simplest thing to do in this situation is to add another field that is unique to use as the primary key. So why won't adding a field called student number, however, work in this case? Well, having added the student number field, each record now has a primary key. However, each student now has 3 different student numbers. Therefore, student number field is not an appropriate solution. We could use what's called a composite key, a combination of 2 or more fields in a table that can be used to uniquely identify each record. Now, uniqueness is only guaranteed when the fields are combined. Individually, the fields do not generate uniqueness. But what is the potential problem with using the name and the course number field as our composite key? Well, as it stands, no 2 students with the exact same name could ever take the same course. We could add the date of birth field into our composite key. This still isn't a perfect solution, as no 2 students with the exact same name and date of birth could ever take the same course. The solution still needs work, but let's go with it for now and see if we can find a better one as we further normalise the database. The final rule has been met, so our table's now in first normal form. To get to second normal form, a table should follow 2 rules. The data's already in first normal form, and any partial dependencies have been removed. To put it another way, each table should serve its own purpose. At the moment, our table has the dual purpose of storing both student and course details. If we split our table into 2 tables, we'll need to create a relationship between them. We must then fix any many-to-many relationships that we've produced as a result. So as we know our database is already in first normal form, the only rule we have to worry about is removing partial dependencies. But what exactly do we mean when we say partial dependencies? Well, first, let's explore what we mean by dependency in a table. In this table, car registration is our primary key, as it's unique for every record. That means we can use car reg to fetch any record from this table. Even in situations where the make and or model of the car is the same, as long as we know the car's registration number, we can fetch the right record. For example, I can ask for the model of car reg BL16UDK and get the answer. I can ask for the colours of cars with registration numbers M176HEL and BP38YTE, and I will get the answers. All we need is the car reg. Every other field can be fetched using it. In other words, every other field depends on the car reg field. This is what we call dependency. A partial dependency means one or more of the fields depend on only part of the primary key. This issue can arise if the primary key is a composite key comprised of more than one field. The fields course name, lecturer initials and lecturer's name are only dependent on the course number. None of them are dependent on the student's name, date of birth or gender. We found a partial dependency as these fields are only dependent on part of this composite primary key. To fix this, we'll split the table at the course number field and move the remaining data into a new table. This is a better situation. We now have less repeating data and no partial dependencies. However, in the process, we've created a many-to-many relationship. So let's just quickly go over a little trick for how to spot when to split a table. Ask yourself the question, what can I infer from this field? If a field or group of fields can be inferred from a field that isn't the primary key, they are key candidates for splitting into a separate table. So here we can say, well, if I know a student is called Tony Gibbons, can I infer their date of birth or the course they're taking? Well, the answer is no. If I know a student is born on a particular date, can I infer their name or gender? No, of course you can't. If I know a student is male, can I infer their name or the course they're taking? No, of course you can't. If I know a student is studying course F451, can I infer anything from this information? Yes, I can infer the course name, the lecturer's initials, and their name. Okay, so let's return to our linked example. We've created this many-to-many relationship, which, as we know, we can't have in a real database. But luckily, fixing a many-to-many relationship is very easy. We also still have a lot of repeating data in the student table and this large composite key. A neat primary key, like student number, would be much better. So once we spot a many-to-many relationship, we can fix it by creating a linking table, assigning the primary keys from the two initial tables as the composite key for the new linking table. And then we flip the many-to-many crow's feet relationship to become two one-to-many relationships joined by the new table. So create a linking table, assign the primary keys from the two tables to be a composite key in the new table, flip the crow's feet relationship to become two separate one-to-many relationships joined by the new table. So we can see here which course does Matthew Robinson take. We can clearly see we look at Matthew Robinson on the left. Student ID number 2 takes us to the linking table, but then in the linking table we can have 3 entries for student number 2 because student number on its own is not unique. And we can see that he takes 3 courses, G403, Q947 and P202, and they link off to the course number table. Again, course number is not unique in that middle table, but the combination of the student and the course is unique. We have solved our many-to-many relationship problem. It also works the other way. We can answer the question, which students take the computing course? So starting in the table to do with courses, we see that computing is F451. That goes back to our linking table, and we can see there are 2 entries for F451. F451 is not unique because course number on its own is not unique. They link to student 001 and 003. Again, student 001 and 003 are not unique in the middle table, but the combination of the 2 fields is. So to get to third normal form, a table should follow 2 rules. The data is already in second normal form, and any transitive dependencies have been removed. Another way to say this is that we need to remove any non-key dependencies. A non-key dependency is one where the value of a field is determined by the value of another field that is not part of the primary key. A phrase to help you remember how to get your database to third normal form is all fields are dependent on the key, the whole key, and nothing but the key. Once again, the aim is to remove repeating data. So we can see here the value of the name field is determined by the primary key field student number. In other words, we can say student 001 is Tony Gibbons. The value of the date of birth field is determined by the primary key student number. In other words, we can say student number 001 was born on the 15th of the 2nd, 1979. We can also say the value of the gender field is determined by the primary key field student number. In other words, we can say student number 001 is male. This table is in third normal form as there are no transitive dependencies. Or to put it another way, all fields are dependent on the key, the whole key, and nothing but the key, which in this case is student number. Now this linking table in the middle must already be in third normal form, as the 2 fields that make it up form a composite primary key and there are no additional fields. So let's look at the last table, course. The value of the course name field is determined by the primary key field course number. In other words, we can say course number F451 is computing. The value of the lecturer initials field can be determined by the primary key course number or the course name field. In other words, we can say lecturer CSA teaches computing, which is F451. This is a non-key dependency, as it can be determined by the value of a field that's not the primary key. The value of lecturer name field can be determined by the lecturer's initial field. In other words, we can say the lecturer with initials CSA is Craig Sargent. This is another non-key dependency, as it can be determined by a value of the field which is not the primary key. This table is not in third normal form, as we've found two transitive dependencies. Or to put it another way, all fields are not dependent on the key, the whole key, and nothing but the key. All the tables are now in third normal form. In moving from first to third normal form, we've gone from one single table, a flat file, to a 4-table relational database. We've removed repeating data, and each table now serves a single purpose. So here on the screen is a quick recap of how to get your tables from first, second to third normal form. You might like to pause the video and take some notes. So let's look at another example. This table contains multiple choice questions. Each one has a correct answer and 3 incorrect answers. The table is also storing the question topic, the question difficulty, whether an answer is correct, and the number of marks available. Let's normalise the table to third normal form. So to get to first normal form, we follow 5 rules. All field names must be unique. They are already. Values in fields should be from the same domain, and they are already. Rule 3, value in field should be atomic. Well, the values in the answer field are not always atomic. Some entries contain more than one answer. We've now made the answer field fully atomic. In doing so, we've increased data redundancy but satisfied Rule 3. No 2 rows can be identical. Well, they aren't. And each table needs a primary key. Well, we've made a composite primary key out of the topic, question and answer fields, as we know they'll be unique. We'll attempt to improve the situation as we further normalise the table. Our table is now in first normal form. So to get to second normal form, the data is already in first, and any partial dependencies have to be removed. Well, the question field is only dependent on the topic field, so we've found a partial dependency. The difficulty field is only dependent on the question field. We found a second partial dependency. The correct and mark fields only dependent on the answer field, so we found a third partial dependency. We've now split our database up. We've moved the topic field into its own table and added a primary key, topic ID. The question table only has the question and difficulty fields remaining. We've added the primary key, question ID, thus removing our previous composite key, and added topic ID as a foreign key so it can link back to the topic table. And we've put the answer, correct and mark fields into their own table, added the primary key answer ID, and added question ID as a foreign key to link back to the question table. To get to third normal form, we have to be in second normal form, which we are, and make sure that any transitive dependencies have been removed. The mark field is dependent on the correct field, i.e. the mark is dependent on the answer being correct or not. This means it's susceptible to becoming inconsistent. An incorrect answer should never be worth a mark. This is a transitive dependency. Remember, to be in third normal form, all fields must be dependent on the key, the whole key, and nothing but the key. We've moved the correct field into its own table and added the primary key, mark ID, which we've also added as a foreign key in the answer table to link back. The table is now in third normal form. So there is the finished diagram, both showing you the entity relationship diagram and the textual description at the top. We can say that one topic has many questions and one question has many answers, and a mark can be applied to many answers. Having watched this video, you should be able to answer the following key questions. What is the purpose of normalisation? How are first, second and third normal form defined? And what are the rules of first, second and third normal form? Okay, so that's all you need to know for the exam, and this has been one of our longer videos, but if you want to know a little bit more, then please pop your pen down and carry on listening. Typically, ensuring your table complies with third normal form is more than enough to ensure good design practice and certainly good enough for the exam. However, you can normalise your tables into higher normal forms. These higher normal forms address far fewer common data problems. They're more complex and presented here purely for reference and completeness. So after third normal form, we have what's called Boyce-Codd normal form or BCNF. And with this one, all determinates have to be candidate keys. Candidate keys are any fields that can be designated as the primary key. BCNF can be thought of as a new style of third normal form. It was introduced to cover situations that third normal form does not address. A third normal form table that does not have multiple overlapping candidate keys is said to already be in BCNF. After BCNF, we have fourth normal form. So the extra rule here is there are no multi-valued dependencies. A multi-valued dependency occurs when for each value in field A, there's a set of values for field B and C, but fields B and C are not related. And then finally, we have fifth normal form. This extra rule says there must be no cyclic dependencies. Now, a cyclic dependency occurs when you have a multi-field primary key consisting of 3 or more fields. For example, let's say your primary key consists of fields A, B and C. A cyclic dependency would arise if the values in those fields were related in pairs of A and B, B and C, and A and C. Now, the truth is, there are times when you might want to break the rules or, shock horror, denormalize your data. You may sometimes want to put the data in 2 normalized tables back into one denormalized table or store fields that break the rules. The reasons behind this are often performance related, e.g. improving the speed at which queries run. This would be a conscious choice and represents one of the beauties of normalisation. Properly normalised tables can always be put back together with no loss or gain of data.